Morning, physics students. It's your favorite physics teacher here. I'm going to show you a really cool apparatus called a current balance. We're going to use it to verify the Lorentz force when a current carrying wire cuts across a magnetic field. So I'm going to show you what the setup looks like in the next clip, and then we'll gather data for the lab. So if you have any questions, ask, but it's hopefully fairly straightforward. All right, so here is a demonstration or a video of the setup. So let me talk to you about the parts. So first we just have this arm extending out from the stand here. And at the end of it, I can put this little wire, this little, what do I want to call it, plate that plugs into it. And you can see that U-shaped wire that goes down. So that's going to be our current carrying wire that I can simply connect to a voltage supply. And we can measure the amperage through it. All right, so the really cool part is I can slide a magnetic assembly such that this fits perfectly between it without touching the bottom. Okay, so if I look at the reading on the scale, it should read 0, so let me 0 it again. It's very sensitive. And we wouldn't expect anything to be exerted from this wire onto the magnetic field. However, if I turn some current on, right, so let me turn my attention here just to show you we've got some current going through it. We see that the scale now reads some force, and that force is a magnetic force. And what's going on is that reads a positive, so something is pushing down on this magnetic assembly. Of course, that's the wire, and therefore the assembly is pushing up on the wire. So if you were to apply the third-hand rule here, where the positive is coming in from this way, I would point my right thumb this way. The magnetic field is from the red to the white, so I'd have to turn my fingers around. And what I'm trying to get at is, awkwardly, my palm is pointing up. So this wire feels an upward force due to this magnetic field. Therefore, by the third law of motion, this wire pushes down on the assembly, thus registering a positive weight. If I were to reverse the polarity, so why don't I do that real quickly? Okay, so let's see, this is 0'd again. And if I do that, now we see we have a negative reading, indicating that the magnetic assembly is pulling down on the wire, therefore the wire is pulling up on the assembly, making it appear lighter than normal by just a tenth of a gram, but it's still kind of cool to see the third law of motion that way. Okay, so what I'm going to do in the next clip is I'm going to start systematically making measurements for changes in length of the wire as it passes through a given magnetic field, and then changes in the current in the wire for a given length and magnetic field. Okay, so now I have the assembly between here. We're 0'd, so let's plug in, get our current and our force. So our current, we're going to try to keep constant. So right now it's reading 2.56, and it fluctuates a little bit. So that's going to introduce a little bit of uncertainty. And our force is 0.36 grams. All right, so I'm just going to switch out the next assembly, and then we'll repeat this. Okay, so a different wire is in there. I decided we'll make all the measurements of the lengths later because it's just not practical for me to go back and forth like that. Okay, so our current is 2.5153. I want to keep that constant, so let's see if I can make a slight adjustment. And we might just have to live with the fact that, okay, so I'll live with 2.6. Yep, I'll have to live with that. So our force is 0.97. Okay, all right, for our next trial, we have 2.6, so we've kept that constant, and we have a force of 1.02 grams. All right, next length, 1.34 grams, and again, our current is staying between 2.55 and 2.6. Now, I just figured this out about the assembly. This is a new apparatus, so I can easily lift that up rather than have to do the whole thing. So let me see if I can do a continuous. So we'll increase our length. Okay, slide that in. So we don't have to keep turning it off. All right, 1.87. Okay, so I'm going to up the, let's not record that 1.87 just yet. Let's see if we can just up this a little bit. That might be internal resistance of our voltage supply affecting things. So 1.90, I think, is a more accurate reading. And the last length we'll test me show you what that last length looks like. It's actually a clever little design. So the actual length is going to be here plus this. So we have two wires cutting across, but it's not creating a short circuit because I completed the circuit behind there. So we can get double the length of that when we eventually measure. Okay, so just adjusting this. Okay, so we're at 2.54. Let me up it just a little bit. Let's go up, not down. Okay, so that's in our range, and we are at 2.57 grams. So now, let's get the lengths. So we got the first one. The second one, if I line up right there, let's see if this is readable. And I'll try to center it for you. Again, there's a little parallax there. Okay, so it's really hard for you not to see. But that's going to be really close to 2.0 centimeters. Sorry, this is not the optimal way of doing it. Let me try. That's not going to work. Actually, so next one. See if I can center that better. Okay, that's pretty close. Here is the fourth length. It corresponds with the fourth trial. You can see a pattern in these lengths. Here is the fifth one. So again, since we have this little arm up here, we're going to double the length because it's actually cutting across the hole, even though it doesn't look like it on the upper arm. So whatever length you read for the bottom part, you double that for this part. And then for our last one, again, we're going to double the length we see along the bottom. Okay. So there you go. All right, so here's our assembly of wires that we're going to place between the magnets of that assembly. We're going to get the lengths of each one, and I'll just place a ruler up to it if it's practical for me. And then what I'll do is keep a set current throughout, and we're going to measure the magnetic force as registered by the balance. Of course, that'll be in grams, and you'll eventually convert that to newtons. So our first assembly is right here. I don't know if I can do this. If I can't, then I'll just tell you what the distance is. So we're measuring the length that cuts across the field. So it's that lateral length. So if I measure from center of the wire to center of the wire across from left to right, I know I got to tilt it a little bit. So, all right, so you can kind of see what that length is. And if you don't see it, I'll tell you it's 1.0 centimeters. So record that. Maybe off to the side of centimeters, but we'll want to eventually convert that to meters. Okay, so now we're going to put it here. For the second part of the lab, we're going to now test how current affects the force. So this is much simpler. We're going to keep the length the same. We're going to use the last length, the one that should have recorded as about 8.0 centimeters. And I'm just going to change the current in certain increments, probably around a half an amp for 5 or 6 measurements, and then we'll get the weight. So it should be much smoother than the last one. So let's jump right to it. So I got things hooked up, it's zeroed. Okay, so let me go to my power supply. I'll go to about a half an amp. So 0.45 amps gives us about 0.45 grams. Interesting. Let's crank it up. All right, let's settle on 1.11 amps, 1.11 grams. I was not expecting that. Let's see if this continues. 2.03 amps. Oh, there we go, 2.0. Wait a second, what's going on here? Our current keeps changing. 1.99, 1.99. So, all right, we'll live with it. Settle now. Okay, well, you decide what you want to read from that, and here are the corresponding masses. I don't know why it's being erratic, but oh well. Okay, I think this will be the fourth trial. Okay, I'm not going to try to go above 4 amps. It's probably not good for the wire. Then let's do one more trial. Okay, there you have it. So hopefully the analysis goes smoothly. I've tried to make the directions as clear as possible. If you have any questions, always ask.